So we're going to work here on section 7.2, but first let's do some review and some previewing of where we're going. So to review, in chapters 2 and 3, we use descriptive statistics when we summarize data using tools such as graphs and statistics such as mean and standard deviation. That's what we did back then. In chapter 6, the last chapter we just did, we introduced critical values. Very briefly at the end, we talked about Z alpha, and this denotes the z-score with an area of alpha to its right, so in the positive tail of the normal distribution. So for example, if alpha is 0.02, where's my pen? There it is. So let me draw a picture real quick. So if we have a bell curve, and in the right tail we have this area, alpha. If that area is 0.025, then the critical value cutting off that area, so this value right here, is 1.96. Okay? So we talked about that briefly last chapter. This chapter is going to present the beginnings of inferential statistics. This is going to involve two major activities of inferential statistics. Number one, we're going to use sample data to estimate the values of a population parameter. So you might have a sample, you find the mean of that sample. How well does that mean do at, well, estimating the population mean? We're going to build a interval that tells you how well it is estimating. Okay? Number two, we're going to test hypotheses or claims made about population parameters. That's chapter 8, but we're getting there. We introduced methods for estimating values of these important population parameters, proportions and means. So that's going to be chapter 7. And we also present methods for determining sample sizes necessary to estimate these parameters. So sample size, we're going to be trying to determine how much we need to sample to get a good estimate. So that's what we're going to be doing here. So 7.2. In this section, we present methods for using a sample proportion to estimate the value of a population proportion. Remember, in real life, most times you cannot study a whole entire population. So instead, you go get a sample, and that sample you can calculate a statistic of. How well does that statistic approximate the population parameter is a very important question. Well, what we're going to do is we're going to come up with ways of using those sample statistics to estimate population parameters. In this case, we're going to focus on proportion. So number one here, the sample proportion is the best point estimate of the population proportion. So the statistic is a point estimate for a population parameter. In this case, the sample proportion is the best point estimate of the population proportion, meaning it's the best you can get. It's not going to be exact necessarily because it's not using the whole proportion to calculate the sample proportion, but it is using something from the original population. So because we're not using the whole population, it's not exact, but it's going to be the best we can do. We can use a sample proportion to construct what we call a confidence interval. This is chapter 7, confidence intervals. To estimate the true value of a population proportion. So you're going to have a sample proportion, and you're going to use that to build a confidence interval which estimates the population proportion. We should know how to interpret such confidence intervals as well. So we're going to talk about what do these confidence intervals mean and what do we say about them. We should know how to find the sample size necessary to estimate a population proportion. How big a sample do we need to get a good estimate for the population proportion? Alright, so here's an example. The Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. Determine the best point estimate of P. Now remember, P is the population proportion. What we have up above was a sample. From a sample survey of 1,007 adults, we found 85% of them know what Twitter is. So if we wanted to estimate the proportion of the population, what would be the best point estimate? Well, that would be P hat, the sample proportion. So what proportion in this sample recognized what Twitter was? Well, that would be the 85%, but we always write it as a decimal when we write proportions. So 0.85, that would be the best point estimate of P. That's the best we can do to estimate P at this point. Now, we're going to take that point estimate, we're going to build a confidence interval sometimes called an interval estimate. This is a range or an interval of values used to estimate the true value of a population parameter. So on the number line, if your point estimate, p hat, is right here, what we're going to do is we're going to build an interval around that. Somewhere in this interval, we are estimating that the true value of the population parameter lies somewhere in here. So it's always built around your statistic, the p hat, and we are going to be pretty doggone certain that p is actually in there. A notation that you might see is confidence interval simplified or shortened, abbreviated to CI, confidence interval. That's a C and an I there. So this is what we're going to work on. So to do this, you need a confidence level. You have to have a certain level that you want to have. Now the typical ones you can see at the bottom, 90, 95, or 99%. So this is how certain you are that the actual population proportion will be in your confidence interval. So a confidence level is the probability 1 minus alpha, often expressed as the equivalent percentage value. Percentages are what you see at the bottom. The probability that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. Alright, so the confidence level is also referred to as the degree of confidence or the confidence coefficient. Basic idea, it's a level at which you are saying, I have 90% confidence that this interval will contain the population proportion, or I am 95% confident that this interval contains the population proportion. How confident you need to be depends on the situation you're working in, and the more confident you are, well, the bigger your interval will have to be. The less confident, the smaller your interval can be. So you kind of have to balance the two. The size of your interval depends on the level of confidence that you require. Now at the bottom you can see the corresponding alphas. So alpha 0.10 is the corresponding to 90%. Because remember, these percentages are coming from 1 minus alpha. So if alpha is 0.1, then we get 0.9 or 90%. Okay? Alright, make sure you interpret a confidence interval correctly. We must be careful to interpret confidence intervals correctly. There is a correct interpretation and many different and creative incorrect interpretations of the confidence interval. For example, this one. So we're saying that the population proportion is in between 0.828 and 0.872. Somewhere in there we're relatively confident that our proportion lies in there. In the green I've highlighted what the correct interpretation of this interval is. So we are 95% confident. That was the confidence level that this interval was built at. We are 95% confident that the interval from 0.828 to 0.872 actually does contain the true value of the population proportion P. This means that if we were to select many different samples of size 1007 and construct the corresponding confidence intervals, 95% of them would actually contain the value of the population proportion P. Now let me draw a little bit of a picture down here on the bottom. So let's say that this line here denotes the actual population proportion P. Now, what we're doing is we're drawing intervals. So here's one possible interval, here's one possible interval, here's another. So all of these are intervals, and they're intervals trying to approximate P. Okay? Now, if you notice, most of these intervals do cross that line. They do contain P in them, but one does not. That is the 5% that doesn't include P. So when we say we're 95% confident, we're saying that in all possible P intervals that we could build, because remember, every single sample that you take, that's a different place to build your interval at. Different P hat. Every single sample you take gives you a different P hat to base your interval off of. So because of that, all of these are different intervals that we could be working with. We are 95% confident that the one we pick will have our P in it. Because we know there's some chance out there, like that one I circled, that don't have it. So there's a chance that your interval will not be correct at approximating P, but you are super confident. You have a 95% level of confidence. That's very good. Okay. Using confidence intervals for hypothesis tests. Now, hypothesis test we have not talked about yet. That's chapter 8, but this is going to be a relation to that. A confidence interval can be used to test some claim about a population proportion. For now, we do not yet use a formal method of hypothesis. That's chapter 8. So we simply generate a confidence interval and make an informal judgment based on the result. So, what do we need? We need critical values. So a standard z-score can be used to distinguish between sample statistics that are likely to occur and those that are unlikely to occur. Right? So we talked about z-scores last chapter very briefly. It's coming back again. It's coming back in chapter 7 and chapter 8. Make sure you understand these. So, such a z-score is called a critical value. Critical values are based on the following observations. Number 1, under certain conditions, the sampling distribution of sample proportions can be approximated by a normal distribution. Now, we have to have normal distribution in order to continue our problems. So we're going to talk about what's required, but we will have normal, otherwise we can't do anything. A z-score associated with a sample proportion has a probability of alpha divided by 2 of falling in the right tail. So let me translate this. So we have a bell curve. They're saying that we have 2 tails here. Alpha divided by 2 is the area in one tail, and alpha divided by 2 is the area in the other tail. Together, the 2 tails, if you add them together, are the total area alpha. Okay? That is going to leave us with 1 minus alpha in the middle. So this is our confidence level. This is, oops, where'd my camera go? This is our confidence level in here. The tails are very small chance that we're actually outside of there. Okay? Alright, number 3. The z-score separating the right tail region is commonly denoted by z alpha divided by 2. Small change. Instead of just denoting alpha down there on the z, we're now doing alpha divided by 2 because that's what we're interested in. We're interested in the total area alpha divided between the 2 tails. So, 1 tail is what you put at the bottom of the z. When you write a critical value, that number at the bottom of the z is 1 tail's area. So, the z alpha divided by 2 is a critical value because it is on the borderline separating z-scores from sample proportions that are likely to occur from those that are unlikely to occur. So, likely are in the middle, unlikely are in the tails. Why are these unlikely? Because these are really small tails. These are just a tiny percentage, so maybe 0.5 or maybe even 0.05. They're very small. The chance of being there is ridiculously small chance. So unlikely is the tails. Alright, now, let's review here. If you have a tail area of 0.025, that means your alpha, well, remember, 1 tail is 0.025. That means 2 tails would be 0.05. This is your total alpha. If 1 tail is 0.025, 2 tails together is 0.05. Then 1 minus that gives us our confidence level, 95%. So, critical values associated with this level of confidence, well, you would look up in your table the area to the left. So you could look up the left tail if you wanted to, and you would get the left end critical value. Notice it's a negative. The right end critical value is simply the positive version of that. So this is what you would look up in the table. Okay, remember, you look up in the middle of the table because that's an area, and you look at the edges to get your z-score. Okay? Now, these are the 3 most common critical levels, and they are corresponding alphas and critical values. So if you wanted to, what you would do is you would divide by 2. Alpha divided by 2 is the area to the left, that would give you a negative z alpha divided by 2. Just change the sign and you'll get all these up above. Okay? Alright, margin of error for proportion. So, what we're doing here is we're getting a sample. For that sample, we get a sample proportion. We're then building an interval around that. Why do we have to build an interval? Well, one sample is not telling the whole story. So, we take that p hat, that sample proportion, and we say, well, it's probably not exact because it's a sample. So let's build an interval around it. That interval is taking care of any error that might be involved in p hat. So that's what this is calculating here. This is calculating the maximum error there could be for p hat to reach p. Now, this is not necessarily going to be exact. Like we said, this is at a certain confidence level. So this is the error calculation at whatever confidence level you set. And that determines how big your interval is. Your confidence level determines your alpha, which determines your z-score. So this is where your confidence level comes in. Okay, p hat and q hat, those come from your sample, and n is the number in your sample. How many sample values did you have? So you're going to calculate this. You're going to have a critical or a confidence level, 90%, 95%, 99%, somewhere in there, and you're going to get your z-score for that. Then you multiply by the square root of p hat times q hat divided by n. This is the error. What you do with that error comes next. So, in order to build the confidence interval we're trying to build, you need 3 conditions to be satisfied. Number 1, the sample that you have, that you're working with, must be a simple random sample. Meaning every single sample possible should have had equal chance to be the sample chosen. Number 2, you need the conditions for the binomial distribution to be satisfied. And in case you've forgotten what those are, they're all listed here for you. Okay, so review. You need a fixed number of trials, an n value. The trials must be independent of each other. There are 2 categories of outcomes, success and failure. And the probabilities must remain constant for each trial. So probability of success remains the same. Number 3, there must be at least 5 successes and 5 failures to use this as a confidence interval. Here's your confidence interval. No is not bad. Don't freak out. Okay, you're fine. Now, this is what you're trying to estimate. So that will always say p because you don't know p. You're building an interval to estimate p. What you do is you take your p hat. Remember, this is your sample. And you're going to subtract the error and you're going to add the error. That builds an interval out from p hat. So you have p hat, and then you go plus e and minus e, and you have an interval now. E is right on the bottom again. It's the same thing I just talked about a minute ago. Now there are a couple different ways to write this interval. One is the one at the top with the interval notation, or inequality notation. The second one is just plus or minus, meaning, well, you add and you subtract. It's a shorthand notation for what we're doing. And the last one is interval notation. So the parentheses mean the ends are not included, just like there's no equal signs on this inequality here. No equal signs. And those are just 3 different ways to write your answer. It's up to you which one. My stat lab, I think it rotates which one they ask you for. We're going to do an example in a minute, so hang in there. Now, when you're dealing with p, just like probabilities, you're going to still round to 3 significant digits. So all the zeros and then 3 numbers. Procedure for constructing a confidence interval for p. Okay, so here we go. Number 1, verify that the required assumptions are satisfied. You have to have the simple random sample, you have to have the binomial requirements, and you have to have c. This is the important part. You have to have normal distribution, and this tells you the requirement to being normal. N times p must be greater than or equal to 5, and n times q must be greater than or equal to 5. Meaning, you have to have at least 5 successes and at least 5 failures in your trials. If you don't have at least 5 of each, you can have 150 and 3,000. That's fine. You have to have at least 5 of each to be able to build this confidence interval. Number 2, you refer to table A2. That's your z table, your normal distribution table, to find your critical value. And then number 3, you find e. 4, you build your interval. You add E, you subtract E from the p hat. And number 5, you round. Do not round until you get to the end. Don't round to p hat, don't round E, round at the end. Here's an example. So we're going to do one all together, very slowly. In the chapter problem, they noted that a Pew Research Center poll of 1,007 randomly selected adults showed that 85% of respondents know what Twitter is. The sample results are n equals 1,007 and p hat equals 0.7. Okay, so that's a typo, so let me fix that real quick. That should actually be 0.85. That's why that didn't make any sense to me. Oops. There, all right. Okay. So, the sample results are those. Now, part A. Find the margin of error E that corresponds to 95% confidence level. So, we need to find E. That's the next step. Let's do this. Now, in order to build E, though, you should check your requirements. The requirements are all listed here. We're assuming that it was a simple random sample. They had a fixed number of trials. They did, 1,007. The trials are independent of each other. Well, every adult they asked, we're assuming that they were independent of each other. Because it doesn't really, well, it's peer research. They should have done it correctly, you hope. We don't know. We're assuming most of this, just so we can do the problem. So unless it is point blank, obviously not satisfying a requirement, we're going to assume it always is. The probability remains the same for every person, so every individual should have had the same probability of knowing what Twitter was. And we're noting, very important, the number of successes and failures are both at least 5. How do I know that? Let me go back. Well, there were 1,007 participants. 85% recognized what Twitter was. That leaves 15% that did not know what Twitter was. If you find 85% and 15%, both of those are, in fact, bigger than 5. So let's just check this. So 1,007 times 0.85. That gives you 85%. Calculator. If I can find my calculator. Oh, there it is. So 1,007 times 0.85. So that means I have 855.95. And if I do 1,007 times the 15%, 0.15, that leaves me with 151.05. Notice both of these are bigger than 5, or at least greater than or equal to 5. So we do assume that we have a normal distribution. So that's the requirement to having normal when you talk about proportions. Alright, so we can do this formula. So here we go. To find our Z, we need our confidence level. So what was our confidence? 95%. So 95% confidence tells us that alpha is equal to 0.05. The rest of it. So if there's 95% confidence, alpha is the tails, the not so confident part that could be an error. Now, alpha divided by 2 is the area in one tail. So that's 0.025. So let me go get my Z table, and we're going to look that up in the Z table and check to make sure we know how to do this. Alright, here's my Z table. Now, 0.025. That's not on the positive Z-score. Remember, this is the area to the left, so we're looking for the left tail, the negative Z-score. So 0.025 right there. Okay? Now that has a Z-score corresponding to it, which is right there. So 1.96. Now that's the left tail. The right tail would be the positive value. So let me clear this. So 1.96. Go back to the PowerPoint. Put my pen back. So Z alpha divided by 2 is 1.96. Now, Z is always the positive. We're going to take care of the minus situation when we add and subtract the E. So just be careful there. So this is 1.96. Always use the positive when you talk about Z alphas. Square root. P hat, they told us, let me go back. P hat was 0.85. So that's our 0.85 for P hat. Q hat is 1 minus P. So that's 0.15. So write that on the side. Q hat equals 1 minus P hat. That's how we get that. Divide by N. N was the 1,007 participants. Be very careful in taking this in your calculator. Everything inside the square root must be in parentheses inside of your square root. So 1.96 times a big old square root, and in parentheses we put the 0.85 times 0.15 divided by 1007. Uh-oh, I missed something. Divided by 1007, close parentheses, equals. So I just entered it all at once, 0.022054. Now, try and keep a bunch of decimal places because this is not the end of the problem. For this question, for part A, if I were entering it into my stat lab, I would round it. And 3 significant, it should be about good. But if I'm going to use this in part B, I need to keep as many decimal places as possible, which we are going to use it in part B. So we need to fill everything in here. P hat, that is the 0.85. 0.85. We keep the P. The E is what we just found in part A. So part A goes in here. So I'm going to do 0.85 minus my E that I just found, 0.02205, less than P, less than 0.85 plus 0.02205. Alright, so we keep our P in the middle. And then we round to 3 significant figures. So 0.828 and 0.872. There you go. So this is our confidence interval. Now part C. Based on the results, can we safely conclude that more than 75% of adults know what Twitter is? Well, let's see. What does this say? This is saying that the proportion of adults, P, who know what Twitter is. Now, this P is for all adults. This is claiming that the proportion of adults who know what Twitter is somewhere between, if I change it to percentages, 82.8% and 87.2%. Well, can we claim that at least 75% of all adults know what Twitter is? Well, based on this, it should be way over 75%. It should be somewhere between 82.8 and 87.2. So the answer to this would be yes. Because we are 95% confident that the actual percentage is between, what was it? 82.8% and 87.2%. There you go. Now there's a chance it's less than that or more than that, but it's a very small chance, only a 5% chance. Part D. Here's one statement that summarizes the results. 85% of U.S. adults know what Twitter is. That percentage is based on a Pew Research Center poll of 1,007 randomly selected adults. In theory, in 95% of such polls, the percentage should differ by no more than 2.2 percentage points. This is your E value that you calculated, in case you're wondering where that came from. In either direction from the percentage that would be found by interviewing all adults in the United States. So, that would be a good summary of what we just did. We talked about the original sample, and then we talked about, well, what would be a decent way of approximating your actual population percentage. Alright, sample size. Suppose we want to collect sample data in order to estimate some population proportion. The question is, how many sample items must be obtained? So you're going to get a sample. The question is, how much do you need? You want to estimate a population proportion, but you don't want to be too far off. If I only get 5 frogs from my frog pond to estimate the size of my frogs, that's not a very good estimate. That's only 5 out of who knows how many frogs I have. It's ridiculous. So how many is a good number? Here's what happens. We take our error formula you see at the top that we use to build our confidence interval and solve for n using algebra. So they divide by the z, they square, then they flip stuff over, and then you don't have to do the algebra. The formula is there. It will be on your formula sheet as well. That formula is solved for n. N is the number you need in your sample. It's based on z, which is your confidence level that you want. How confident do you want to be in your point estimate? It's based on your sample p hat and sample q hat, and it's based on your error size. So, now there are 2 situations that could happen. P hat, well, that's based on your sample. There are going to be times where you have a p hat. Maybe it's a starting point. They did a small sample and they want you to use that p hat value to determine how big of a sample you really need. Or there might be times where you aren't given a p hat at all. If you're not given a p hat at all, you're going to be using 0.25 to replace p hat times q hat. If you don't have p hat or q hat, we're going to use 0.25 to replace both of them together. That's the only difference between these 2 formulas. Alright, round off rule for determining sample size. So, if the computed sample size n is not a whole number, so from this formula you get an n value. If it's not a whole number, you must round up to the next larger whole number. Okay, you can't have a part of a sample item. You can't have half a frog in your sample. It's not very fair. So you must round up to the next larger whole number. Alright, we're going to do an example. Most companies are interested in knowing the percentage of adults who buy clothing online. How many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? So, part A. Use a recent result from Census Bureau. 66% of adults buy clothing online. Now, what are we being asked to find here? You must know what you're being asked before you can do anything. How many? This is a count. This is your n. We want to know what n is. So, for n, whatever it means I do, n equals z alpha divided by 2 squared times p hat times q hat divided by e squared. Now, we are being told a 95% confident. We've already looked that up. If you recall, that was 1.96. That was your z score for that confidence level. So I can use that here. So 1.96 is my z. Don't forget to square it. P hat. We're told in part A to use 66% as our sample. So that's what we're going to use for our p hat, 0.66. Q hat is 1 minus that. So that would be 0.34. And then we divide by E. E is how off you can be, or how close they need you to be, depending on how they phrase it. So it says in error, that's your error, by no more than 3 percentage points. So 3%, that would be 0.03. This is your error. So that is how big our interval can be. They don't want it to be any bigger than that. They want it to be smaller, if anything. So that's our E, 0.03. Square it, and then we grab our calculator and we punch all of this in. So I get, when I punch all that in, 957.8389. Now, as we said before, if you don't have a whole number, if you have a decimal, you must round up. So 958 would be our N value. So what this means is you need to sample 958 adults, and that is how many you need to have 95% confident in an error only of 0.03. Very small interval for your confidence. Okay? Part B is a little different. Assume that we have no prior information suggesting a possible value of the proportion. No p hat, no q hat. So for part B, you have to use the other formula for n. So we still have z alpha divided by 2 squared, but instead of p and q hats, you're going to use 0.25. Make sure I got 0.25 right? Yes, 0.25. And then on the bottom, you're going to have the e squared. Z is still 1.96. Don't forget to square it. Times 0.25. Divided by e is still 0.03. Nothing's changed except for your p hat and q hat. Let's see how this affects our numbers. So 1.96 Alright, now I get 1067.11. Round up, 1068. So by not having any information to base our sample size off of, we actually have to sample more. What would be better in real life? Would you rather have to sample 958 or rather sample 1068? Remember, sampling costs time and money. So you would rather sample the smaller amount. So it's actually better to have some value for p hat and q hat to base your starting point off of knowing how much you actually need to sample. One last thing. If you are given a confidence interval, so if you have a confidence interval and you need to find, so remember this is the p hat minus e less than p hat plus e. So if you have these two values here, this is your upper and lower confidence limits. You can find the original p hat or the original e, the margin of error, using these two formulas. If you want p, you add those two circles together and divide by 2. If you want e, you subtract those two circles and divide by 2. And that's just if you need to go backwards. Alright, that's the end of 7.2. Do your homework. If you have any questions, email me. Press the Ask My Instructor button. I'm happy to help you. But go do your homework because the next two sections are actually easier. Once you understand proportion, the next two go much quicker. So go understand proportion and then go on to the mean and yeah. Okay.